Hello again. In this video, we're going to find the derivative of the general logarithmic function. Now, in a previous video, we did find the derivative of the natural log function when the base of the logarithmic function is base e. In this video, we're going to extend that idea so that we can find the derivative of any logarithmic function no matter what its base is. Okay, so Theorem 318 says that if b is positive and not equal to 1, which are the conditions that we need for a base for a logarithm. Okay, so if b is positive and not equal to 1, then the derivative of log base b of x is 1 over x times the natural log of b. And this is true for positive x values only. It also says that the derivative of log base b of the absolute value of x is also 1 over x times the natural log of b. And this is true for all x values except for 0. Okay, so what I want to do is show you where both of these derivative formulas come from. Okay, so let's say y is equal to log base b of x. We're going to find dy dx. Okay, but we're not going to find it directly. We're actually going to convert this logarithmic equation into its exponential form. And you may remember how to do this. What we're going to do is we're going to switch the input and the output. So we're going to switch the x and the y. But when we do that, we have to work with its inverse function. And of course, the inverse function of a logarithmic function is an exponential function with the same base as the logarithmic function. And so in this case, base b. And so you can see that y equal to log base b of x is the same as saying b to the y is equal to x. Notice here that the x and the y are being switched, right? Over here, x is the input and y is the output. But over here, y is the input and x is the output. And that's the reason we're using the exponential function. Okay, so we're going to work with this equation, the exponential form of this logarithmic equation. And what we're going to do is we're going to find dy dx from this equation using implicit differentiation. Of course, the first step when you use implicit differentiation is to take the derivative of both sides with respect to x. Okay, of course, on this left-hand side, that derivative is just equal to 1. And then to find the derivative of this right-hand side, we're actually going to have to use the chain rule. Because this is really a composition of two different functions. Okay, so the outer function in this case would be b to the x power. Then the inner function would be y, which we're assuming is a function of x. Okay, so that's our outer and inner functions. And now, of course, we have to use the chain rule to find the derivative of a composition of two functions. And so we have to find the outer derivative and multiply it by the inner derivative. Okay, so let's find the outer derivative. Well, the outer derivative is the derivative of this function with respect to x. And if you remember from a previous video, we found this. This derivative is simply b to the x times the natural log of b. Remember, you do have to evaluate this derivative at the inner function. So we actually end up with, as our outer derivative, we actually end up with b raised to the y power times the natural log of b. Remember, in your derivative formula for the chain rule, it's f prime evaluated at the inner function g of x times g prime. So our outer derivative is not just simply the derivative of this outer function, it's the derivative of the outer function then evaluated at the inner function. So we have to substitute this y back into actually the derivative back in for this x. Okay, so it's not b to the x ln of b, it's actually b to the y times the ln of b. Okay, and then we multiply that by the inner derivative, which of course is just the derivative of this inner function with respect to x, which is just dy dx. Okay, and now let's just solve for dy dx by dividing this to the other side. Then we're going to go ahead and replace this b to the y. B to the y is the same as x. Now it's a function of x. Okay, so dy dx is actually 1 over x times the natural log of b, which, of course, y is equal to this logarithmic function with the base b. So we just found the derivative of this logarithmic function. It's just 1 over x times the natural log of b. Right, now let's extend this to the case where we have logarithm log base b of the absolute value of x. This is actually a piecewise function. So log base b of the absolute value of x is equal to log base b of x as long as x is positive, but it's actually equal to log base b of negative x if x is a negative number. That's the very definition of the absolute value of x. Okay, so let's say you find the derivative of this function with respect to x. And let's take the case when x is positive. Well, that's the same as taking the derivative, of course this is a piecewise function. If x is positive, then this log base b of the absolute value of x is simply log base b of x. And we know the derivative of this, we just found it. All right, it's 1 over x times the natural log of b. But if x is negative, then we can replace this log base b of the absolute value of x with log base b of negative x, because that's what it's equal to if x is negative. Okay, and now to find this derivative, we're going to have to use the chain rule again, because this is a composition of two functions, right? It's the log function as log base b function is your outer function, and then your inner function is negative x. And so by the chain rule, we have to take the outer derivative and multiply it by the inner derivative. Now, the outer function in this case is log base b of x. And then the inner function is negative x. Okay, and so the derivative of the outer function, or derivative of f, right, f prime, would be 1 over x times the ln of b. And then we have to evaluate this at g of x to get the outer derivative. So when you substitute g of x into here, right, g of x is equal to negative x, you're going to get 1 over negative x times the ln of b. Okay, so that's our outer derivative. And of course, the inner derivative g prime is just -1. So you can see what's going to happen here. The negative here and the negative here are going to cancel back to a positive, and so you just end up with the same answer. So it really doesn't matter whether x is positive or negative. The derivative of this log base b of the absolute value of x is 1 over x times the ln of b in both cases. And so that's what the second part of that theorem says. Now, of course, there are some restrictions on this. X is not defined if it's equal to 0. And maybe we could include that in this piecewise function. It's undefined if x is 0. And that's just because this logarithm, log of 0, you can try this on your calculator, log of 0 is undefined. Okay, now for this one, the restriction is b must be positive. I'm sorry, x must be positive. Again, that's because the domain of the logarithmic function, x must be a positive number for the logarithmic function to exist. You can't plug in 0 or a negative number into this logarithm. It's undefined at those values. So x must be positive. Now notice over here, when you take the absolute value of x over here, it turns it into either a positive number or potentially 0, but couldn't even be 0 because that's undefined. So it ends up being a positive number here, and you can take the log of a positive number. You just can't take the log of 0, and that's why it's not included in this particular case. Okay, so that's theorem 3.18. Okay, so I hope you found this video helpful. Thank you for watching.